Alright. A wedge of mass 11 kilograms is held on the ground with base horizontal and smooth faces at 30 degrees and 45 respectively to the horizontal. Oof. There's a pulley and everything. This is glorious. This is the type of question you want. Now, I'm just trying to get something into your head right now, right? What would happen if you're on a cliff face, alright? And there's a pulley here. Okay? And you're pulling somebody up. So here's somebody dangling off the edge, and you're up here pulling him upwards. What way is the tension pulling you? So tension's pulling this dude up, but the tension is pulling you across. Is that okay? Now, for argument's sake, instead of pulling somebody up using your arms, now this sounds stupid, alright, but just bear with me. You lasso it around your head, alright? And there's one dude this way, alright? He's going up, and this guy is on his way down because of the differences in the weight. What are you experiencing? What forces are you experiencing on your head right now? You're experiencing rope burn, but what else are you experiencing? You're experiencing getting pulled downwards, aren't you? And what else would you be experiencing? If there's components going right and left, one of them might pull you more left than the other one. Is that alright? So the first thing I want to get through to you is about the wedge itself. Is imagine we have two tensions. Sorry, well, the same tension in different directions. Is that okay? What way would the wedge be experiencing that? The wedge itself. Anybody? So the wedge itself would be experiencing this. It'd be experiencing one of the T's doing this, and the other T doing that. Is that okay? And to be at different angles as well, right? So that one would be at 45 and this one would be at 30. Is that okay? And what about alternate angles then? What do you reckon? That'd be 30 as well, wouldn't it? So what does that make the two T components there, do you reckon? And we know. So it will be basically, if that's 30, and that's T, you're talking about T cos 30 going to the left and T sin 30 going down. Is that alright? And what's T cos 30? Root 3 over 2. T and T sin 30 is anybody? A half T. That's what the wedge experiences. That's how the wedge experiences the tension. Is that okay? Now, what about here? Anybody tell me? T over root 2. Yeah, it's 45 degrees, isn't it? So one of them's T over root 2, and the other one is also T over root 2. Do you see the difference in those 2 years between the standard of the part B's? Like one year you'd be like thinking twice about doing it, and the other year you'd be like, yeah, I'm definitely doing that. You know? So that's going to be T over root 2 and T over root 2. Acceleration A. But what do we know about, acceleration B. What do we know about acceleration B? We're going to replace it with 0 because it doesn't move. Is that alright? So it doesn't move, B is going to be 0. Alright. Next part. What does that also mean? Do you remember we usually resolve the acceleration into its components? Does everybody remember that? Yeah. But what's going to happen? The components are all going to be? 0. They're all going to be 0, aren't they? So I don't actually have to resolve its components whatsoever. We're going to pick another question next where we do have to resolve components of two different faces. But the B value the b value is going to be 0 no matter what. So we're technically wasting time. We're technically wasting time resolving the b components, aren't we? So because we know b equals 0, we can actually technically, as you said, treat it like a plane now, because we know that the b components are always going to be subbed in with 0. So we're all right at the moment. Okay, now let's draw these guys in. So what do we reckon here? What angle do these come down at? What's the weight? 5g. So what about here and here? Just the 30-degree side, so? Anybody? 5g cos 30, anybody? Is 5 root 3 over 2. G. 5 sine 30. 5 over 2g. No bother. Okay. What about the green and reaction force? Try and call it reaction force R. Is that alright? Do you want to call this reaction force X? I don't like using S because it just looks too much like my number 5. Alright? It's true. It's really confusing when you're in a hurry. Alright. What do we know about the weight of the second particle? 7g. What was it? 7g. Alright. And what can I break that up into? 45 degrees, isn't it? Yeah, 7 root 2g. 7 over root 2g and 7 over root 2g. Alright. I'll tell you what. I'm going to grab this and I'm going to bring it onto its own. Thank you, sir. I'd like to say that makes things better, but it probably doesn't. Alright, let's make some equations. What's the goal of the question again? To find the acceleration of what? To find the acceleration of the particles. Do they have a common acceleration on the wedge? Yes. Because the wedge is not moving. They have a common acceleration relative to the wedge, but their acceleration would be different if the wedge was actually moving. To explain this, I won't explain this, it'll just make things worse. Alright, so here's what we're going to do. Let's start off with, which one's heavier again? You're 5 kilograms, aren't you? And you're? Who do you think's winning that battle? The 7 kilograms on the steeper incline is definitely winning that battle. Okay? So, A going upwards and A going that way. Is that alright? Now, we'll actually reduce this in size now. We're going to have to make tons of equations out of it. So, here's what we're going to do. Let's start off with a parallel. 5 kilograms parallel, so we'll do these in red. 5 kilograms parallel, what do you reckon? MA equals F. What's the M value? 5. Okay. 5 bracket A. Is there any B component affecting its acceleration? No. Why not? So we didn't actually have to do the wedge diagram, the wedge acceleration this time. So just 5A. Okay, and then after that, what's the F value?
T minus 5 over 2G.
T minus?
Yeah. 5 over 2G.
Yes. T going upwards for the wedge and 5 over 2G acting in the opposite direction. Because we're going up the hill. We cool with that? Why don't we do 7 kilograms downhill? So what do you reckon? 7A equals F. And what's F in this case? What's causing it to go downhill? 7 over root 2 g, and then after that minus t. There's enough here to find the acceleration, isn't there? Just rechecking the question because I'm actually shocked. Alright, this is an easy couple of marks here. We'll take them. 5a plus 7a. Anybody? 12a. T minus t. Gone. 7 root 2g minus 5 over 2g. Now, go to your calculator and do 7 over root 2. Write 7 over root 2, take away 5 over 2, and then divide your answer by 12, and you'll find out where your a value is. You can give it to me in surd or decimal. Just leave out the g, essentially. 0.2 g. 2 what?
204.
So that. Alright, multiply that by 9.8 to 0.204 by 9.8. What? 2 meters per second?
Yes, 2.00.
Alright, awesome. T. We have to isolate T, lads. So I think this one's a nice one, isn't it? See this equation up here? Oh dear, less green, Mr. Kinney. See that one there? What am I going to do with that? We're going to sub in a equals 2. So we're going to get 5 times 2. 5 over 2g, so plus 5 over 2 times 9.8 equals t. And what does that make t, lads? I think it's pretty close to 40, is it? Here, look at the marking scheme at this rate. Sorry, 34.5? We all good. Now, next part of the question. Next part of the question is the vertical force exerted on the ground. Now, this brings us back to this one here. We're going to rub out the numbers a little bit here. Just make this a bit tidier. Okay, so remember we were working here earlier. Okay, just going to make this diagram a bit more simple for us. All right, chop and paste. New page. All right, what we agreed earlier was the following. We agreed that a half t went downwards, a half t over root 2 went downwards. This one pulls to the left, this one pulls to the right. What else lies on the particle? Can you tell me? So what else lies on the wedge? Reaction force R and reaction force X. There's R, there's X. We okay with that? Now, what happens when we break it up into its components? Which one's which? R cos what? R cos 30, which is root 3 over 2 R, and that's a half R. And here? 45 degrees, so it's x over root 2 and x over root 2. We're looking for the downward force. So which are the only ones we're concerned with at the moment? U, and U. The ones going directly downwards. I also left a really big one out as well. Anybody know what it is? What's the weight of the particle itself? Any takers? 11 kilograms, was it? 11 g going downwards. Pick a letter we haven't got in use yet. Anybody? Reaction force? Y. that right? Reaction force Y. Is the wedge sinking into the ground? Is it like drilling into the ground? What does that mean? Y is equal to 11G plus what else? 3 over 2R, yeah. What else? Yeah. What else? Yeah. Okay. Reread the question. These are letters we chose, aren't they? What does that usually mean? You're not allowed to include them in the... You're not allowed to include them in the final answer. Everybody would have a different letter system. It means you got to get rid of that R and X. That's your next job. Get rid of the R and get rid of the X. You cool with that? Now, get rid of the R, get rid of the X. We know T equals 24.5, so that's grand, right? So let's go back a step. Here's our weird equations from earlier. Is there any X's or R's there? No. In fact, you have served your purpose. Done. But what are we going to go after this time? Those were the parallel equations. What am I looking to use now? I'm going to use the perpendicular equations. Keep it red. MA equals F. So what's MA again? We're talking about going this direction here. Alright? Now, quick explanation for you, is alright? Imagine you get knocked over by a car. You're probably wondering where I'm going with this. Okay? Phelan's crossing the road. He's not the best at crossing roads, as I learned in France one year. And
I saved your money.
You did. Alright. And what happens when you get hit by the car? What's your initial feeling? Ouch. And then what happens? You get pushed forward, don't you? But in some cases you go over the top of the car. Isn't that right? Now, and what happens in these movies where somebody like runs after a car, jumps onto the back of the car? What happens when the car drives off with big acceleration? What usually happens? You slide off it, don't you? Okay? Now, imagine, this is actually how I remember this, right? Imagine it's not a car, but it's a joint wedge. So the joint wedge is knocking people over instead of the car. Alright? And it looks like this. The wedge looks like something like this, alright? Now, what happens when you're at the front of the car, like a bug on a windscreen? What happens to a bug on a windscreen when you're going fast enough? Does it slide downwards? Sort of stays there, doesn't it? So this means your force is you're actually getting pushed sort of outwards by the acceleration is sort of pushing you upwards, isn't it? Not the reaction force, but the acceleration is pushing you upwards. So if you're doing acceleration here, the acceleration would be going upwards. If you're including the wedge's acceleration, it would go upwards. What happens if you're at the back of the car? And you're like this. What happens there? The acceleration sort of makes you sink and fall, doesn't it? Alright. So, if you were including, I'm just teaching something to do with the way that. So imagine, for argument's sake, that you'll see this in another question. Imagine the wedge's acceleration is b. In the case of this one, it'll be plus b, plus a certain variation of b because it's pushing you outwards. But in this one here, it will be minus. Okay? Because you're going downwards. One of them you're going downwards and the other one you're going upwards. Depends on whether you're being knocked over or you're at the back of the car or the front of the car. It behaves differently. One of them pushes you with the motion and the other one you fall off from the motion. Okay? Just remember that when we're doing the next question. Alright? Now, in the meantime, because the wedge's acceleration is 0, what happens here? Because the wedge's acceleration is 0, do we need to worry about anything like that? No, because the wedge isn't moving, its acceleration has no influence. Okay? So here's what we're going to do instead. We're going to say F equals ma, no bother. What is the only acceleration acting downwards here? Anybody?
5 root 3 over 2.
Yeah. 5 root 3, sorry, that's a force, my fault. That's not the acceleration. Give me a sec. The A acceleration is parallel to the plane. The B acceleration would be going downwards, but because it doesn't exist, what does that mean?
0.
0, exactly. And what are the two forces over the other side making this happen? 5 root 3 over 2 g minus r. And in this case, r would equal 5 root 2g over 2. Is that right? Now, it's the same for the other side, isn't it? What would be the shortcut now? If r equals that, therefore x must equal that, because the wedge isn't moving. So now you have it here. Will somebody get me those two in decimal mode, please? Just decimal answer will do me nicely here, I think. Or just multiply by root 3 over 2 actually. Whatever your answer is, multiply by root 3 over 2. Because I'm after root 3 over 2r in decimal mode. And I'm also after I'm after x over root 2 in decimal mode as well. So what's the answer for x over root 2?
34.3.
This one?
Yes.
24.3. And root 3 over 2r? Where you multiply this by root 3 over 2 and insert g equals 9.8. Are you all inserting g equals 9.8?
Yeah, 36.75.
36 point? 43, 40, 34, Michael, you remember that? 34.3 and 36.75? Alright. Here we go. Y equals 11g, which is 11 times 9.8. What's the next one?
36.75.
36.75. What's the next one?
34.3.
34.3. T over 2 is 34.5 divided by 2, and the last one is 34.5 divided by root 2. Lob all that into the calculator, and what do you get? We're hoping for a reaction force of 220.5, all going well. Anybody? We got it?
Yeah.
220.5 minutes. Excellent. Alright.